Hi, my name is Gabriel Pachiana. I work for the Fraunhofer Institute for Integrated Circuits, Division Engineering of Adaptive Systems. We are located in Dresden, Germany. I am part of the Virtual Systems Development Group, where we provide the services of system modeling, SystemC or System Verilog, verification at RTL and system level, fault modeling and injection, hardware-in-the-loop simulation and testing, and development of customer-specific design flow and interfaces. I'm going to present our publication, Automated Traceability of Requirements in the Design and Verification Process of Safety-Critical Mixed-Signal Systems. Our motivation is driven by the challenges in the design and verification of safety-critical systems, such as advanced driver assistance systems and autonomous driving. This requires a consistent methodology to comply with strict functional safety standards, such as the ISO 26262 for automotive. The relations between safety goals, requirements, and architectural components are crucial for understanding the system and how its safety is guaranteed. Therefore, the ISO 26262 explicitly states that requirements traceability between these artifacts needs to be ensured. One of the challenges of developing a safe system compliant with such a standard is to generate and adapt a workflow that contains full requirements traceability and state information of all components of the development process, also across different modeling domains and tool environments. Automation is a key aspect to overcome these challenges and comply with certification processes. Also, having full traceability and state information allows to have a complete and centralized view of the project. In this work, we propose an industry-compatible tool flow for an automated implementation of UVM test cases from system-level requirements, including traceability of the verification flow, as well as regression running and publishing the results. The proposed workflow involves three major domains representing different disciplines and processes. These are the requirements engineering domain, the design and verification domain, and the continuous integration domain. At system level, the activities in the requirements engineering domain usually start with the creation of the system requirement specification document. It is a structured collection of information that describes what the system is expected to do, its environment, performance parameters, and its expected quality and effectiveness. The next step is to define a system test case specification document. It collects test cases that are used to test the collection of system requirements and specify the details of the test approach. All the system requirements from the system requirement specification must be covered by test cases collected in the system test case specification. This provides a warranty that the requirement is checked with a specific test case. A system test case contains textual description and details of the test approach, for example, test steps, description of each step, and expected results, plus test records that shows the pass-fail history of the test in the development lifecycle. The proposed workflow extends this definition by adding important parameters of the AMS testing approach for the automatic code generation. This contains parameter values for instantiating the design under verification in the UVM test bench environment, and configuration values for the input stimulus, which are used to define an analog input signal. Now, in order to move from the requirements engineering domain to the design and verification domain, a process is required. This process can be initiated from the requirements engineering tool and executed via scripting, which involves exporting the test cases from the system test case specification, parsing test details, and filling custom test templates of the UVM verification code. The unique ID of each test case is exported from the requirements engineering tool. Then, the UVM code generator creates the test cases adding traceability annotations. This can be seen as the TC_1 identifier here and here. The generated code is automatically committed to the code repository, and the resource traceability script is triggered, which parses the repository for the inserted annotations containing the URL to the reference code line in the repository. This hyperlink is finally inserted back into the requirements engineering tool. In this way, the proposed workflow provides a robust traceability implementation avoiding human errors. In the design and verification domain, the output of the previous script is the stable baseline of the verification test bench, which can be extended by the verification engineers. The only manual work is inside the scoreboard, where the verification engineer has to implement the specific reference model. Now, to connect the design and verification domain with the continuous integration domain, a report is generated that contains the results of each test run as pass or fail. This is also added on the implemented test using the phasing mechanisms of UVM. Finally, the proposed workflow involves reporting the results of the regression back into the requirements engineering tool. This is either done by the CI tool pipeline, or the requirements engineering tool can trigger the CI jobs and automatically pick up the results. When a test of a regression fails, it is marked as such in the requirements engineering tool, and a defect, an issue, or a bug must be created and linked to the system test case. This allows to have a complete and traceable status of the project inside the same requirements engineering tool, closing the loop from requirements and test case definition to test case implementation and running and report the results. Now, moving to the case study, the proposed workflow is demonstrated on a system-level design and verification project, which consists of an automotive AMS circuit. This is a 12-bit, 4-stage pipeline analog to digital converter. In order to apply the flow, different tools and languages are employed, which are Siemens Polarion as the requirements engineering tool, XML and SystemL for exchanging test case information. For design and verification, we use the languages SystemC and SystemC AMS and UVM-SystemC to implement the test cases. We use these languages within the IDE side. The CI tool is Jenkins, the version control system is Git, and the format exchange of the results is JUnit. Here we can see an example of how it looks part of the system test case specification: the generation of the baseline of the UVM test bench and the design under verification, the regression run with Jenkins, and finally the results published in the requirements engineering tool Polarion. In the results, it can be seen an example of a failing test. In this case, the requirements engineering tool creates a defect linked to the system test case. To conclude, we have presented a system design and verification workflow for safety-critical AMS designs. Using the proposed approach, we were able to demonstrate full traceability of the system requirements specification and system test cases from its textual description inside the requirements engineering tool to its implementation in UVM-SystemC. Moreover, the execution of the test cases are automated using a CI tool, and results are published back into the requirements engineering tool. Therefore, the complete state of the project can be monitored and tracked by the requirements engineering tool, such as coverage, as well as pass-fail status of all test cases. It is shown how the proposed automation in the creation of the UVM-SystemC test bench speeds up the verification process significantly and avoids potential human errors that might be introduced by a manual workflow. So, thank you, and if you have any questions, please don't hesitate to ask.